Hey everybody, it's Adam again, and we're going to go on to the next lecture in our Epi and Biostats class. And the next one's going to be about statistical tests. Alright, and so here are the objectives we're going to be covering today, so mostly in regards to the different tests that we're going to be applying to some of the data we'll be looking at in the medical literature. Alright, so the first thing we're going to do is to compare observed versus expected distributions, and some of the tests we can use to see when we're actually looking at data, what the actual results are, and how we are going to compare that to what we would have expected to see based on normally distributed data. So the question is, do the data that we're following, or does the data that we have follow an expected distribution? So for instance, we were looking at a study here in 2007, and they were looking at heart disease, and they're saying it's the most frequent cause of on-duty death and among firefighters. We're trying to figure out why that was. And so one of the things they're doing was seeking to determine if those deaths occurred while actually fighting fires or if they were during some other time. And so in this case, what you would think is that the null hypothesis, meaning there's no difference between one time versus another, is that all the deaths occur randomly throughout the work week and are not actually related to the activity. It's not during their off times or during when they're actually fighting fires. That it's completely random when these heart attacks are occurring. And so they're using data about how firefighters would spend their time to determine the number of heart attacks or number of deaths that you would expect to see versus what the actual data says. And so again, in this case, we're going under the information that 2% of the time they actually spend fighting fires, the other 98% they're doing other things. And so what we can see here from this table, this is the number of deaths resulting from cardiac heart disease among firefighters. And so we have the different duties. So say here, fire suppression. So this is when they're actually doing the actual firefighting, alarm response and return, physical training, and then some other duties. Okay, and so what they're looking at are the actual number of deaths that occurred, and then versus the number that would be expected based on the percent of time they spend doing each of these other these duties. So for instance, if they spend 2% of their time fighting fires, if there was a total of 449 deaths, you expect 2% of those 449 would occur during fire suppression, in which case you would expect to see 9. During, say, alarm response return, 16% of the time they are on the road to a call or coming on the way back. And so based on that percent of time, you expect to see almost 72 deaths associated with that. So what you see is there's some discrepancies here between the number you would expect based on the percent of time that they're spending doing these activities versus what was actually occurring here, right? And so again, here you see they spend the lion's share of their time, 74%, doing other duties, and so you would expect to see 332 deaths during this time period, and what they actually only saw was 111. So there's some discrepancies here, and we can do some tests to figure out, why, is there an actual true difference here, or can we reject our null hypothesis, meaning that all the deaths are completely random, or is there something else going on? And so just based off these numbers here, you would think, so it leads you to think, hey, there's probably an actual difference, but we can do some tests to actually figure that out. And so what we're going to use is what we call the chi-square goodness of fit test. And so again, in the previous example, you saw that the discrepancy seems pretty huge between what is observed and what is expected. It appears it would be very unlikely due to chance alone that the firefighters happen to have those kind of numbers dying off during fire suppression if the null hypothesis were really true. And so we can use this chi-square test. It's going to compare what our observed numbers are, again, so what we actually saw where the firefighters were dying, versus the expected numbers in each of those categories. Okay, so here we're going to see that each number value has to be an integer, and the expected value may be a fraction, though. So we saw in that previous example, they spend 2% of their time doing something, you may have like 9 point something. But for the observed, that has to actually be an integer because that's what we're actually recording from the data set. And then we'll see that the sum of all the observed values must equal the sum of all the expected values. So all the totals have to be equal. And so typically how you see a chi-square table put together is you would have, say, category 1, category 2, so you have there, and then usually a totals row and a totals column. And so looking here, you have your observed column, your expected column. Again, observed is what you actually measured from the data. And so you'd put this here in category A, category 2, and 1, and again the total should just be A plus C in these examples. For here the expected, the total should be B plus D, and you see there's the total rows as well. And again, shows your complete total here in the corner. It's going to be all of the different variables put together. So basically by looking at these expected and observed frequencies, what we can do is actually calculate a p-value using this chi-square test. And it's going to be able to answer kind of the following question for us. If the null hypothesis is true and is kind of completely random, which type of event falls into a specific category, what is the chance, just out of random selection of subjects, that we would find this kind of discrepancy between what is expected we would see out of a normal distribution versus what we're actually seeing in our observed? And so again, the number expected in this case ends up being the null hypothesis. So for instance, if we were saying, hey, if these firefighters are spending 2% of their time fighting fires, then you should see 2% of the deaths that occur happening during that time frame, right? That would be the kind of completely random nature of it. And so if we see a large enough discrepancy here and we do the chi-square test, basically we'll end up coming up with a small p-value. And if that p-value is small, a lot of times less than 0.05, very similar to what we saw previously. That means that the data does significantly depart from those predictions of what we'd expect to see with a null hypothesis. That means there's some other factor that is influencing this, other than just chance alone, that accounts for the large number of deaths to occur while they're fighting fires, right? There's something going on there that is causing it to deviate from that normal expected frequency. And so again, if we see a large p-value on the other hand, that means that the observed distribution does not deviate enough from this theoretical distribution any more than you expected by chance alone. So again, if we were to run the numbers of the chi-square test on the firefighter example, and we were to say, hey, the p-value is say 0.03, means there's only a 3% chance that you should find numbers that deviate from the expected that much, right? So it's very, very low likelihood is due to chance alone. So we can say, hey, there is a true difference here. Let's go ahead and reject that null hypothesis that it's completely random where the deaths are occurring for these firefighters. So how it actually works is basically what we're going to do is we're going to take the observed and expected counts and we combine them into a single value. So for each of the category, basically what we do is we compute the difference between what the observed and expected values are going to be. We square that difference and then divide it by the square of the expected value. And again, I'm not going to have you guys actually do this on the test by any means, but it's important just to look at it and to see what goes into these different values, right? Basically, we're going to add up the result of the first step for all the categories, and the result that we're going to get is going to be this chi-square value. You can see the chi-square variable. And so we also will look at our degrees of freedom. Previously, when we looked at degrees of freedom for something like a t-test, what we saw is that we would use our n minus 1. Here what we're going to use is basically the number of categories we have minus 1. And so again, if the null hypothesis is true, the distribution of that chi-square for our specified number of degrees of freedom is known. Basically what we can do is use a program or table that will find us the corresponding p-value for that chi-square based on the degrees of freedom that we have. So another way of looking at it, if we were to say, here's our observed values, right? So in this case, we're going to look at kind of more generic categorizations. But see, for instance, if we have exposure, people who are exposed to something, maybe something in the environment or some sort of, some sort of influence versus no exposure, and then you're comparing the people that got disease versus did not receive disease. These are other types of comparisons you can do with chi-square tests. So say, here's what our observed values are going to be. So we actually measured this with our sample. And then we can see what our expected values would be. And so you can see basically it gets pretty complicated as far as how they're actually going to figure out what the expected values are going to be. This is normally how you would do it. Basically you would take the people, a number of people that had the disease, so you can see A plus C, multiply it by this A plus B, which is the number of people who had the exposure, and you divide that by the total A plus B plus C plus D. Basically what this is telling you is like, based on just random chance alone, what would be the expected number of people that receive disease or had the disease based on the fact they had an exposure to whatever influence you're talking about. And you can see how these are going to differ. Again, I'm not going to make you do this on the test, but just so you can see how we come up with what the expected values are going to be. With the firefighter example, it's a lot easier just because you could say, well, here's the percentage of time they're doing X, Y, and Z, multiply that by the number of deaths and you get your expected column. Here's another way of doing it where you can actually look at the observed values and figure out what you would expect to see just based on chance alone. And so a little bit later on in this series of lectures, we'll talk about some other places where chi-square tests can be very useful for comparing expected versus observed frequencies. But moving on, we're going to start to compare proportions now. And so we can do this both with prospective and experimental studies, and we'll see how we can do that. So one of the biggest questions that gets asked a lot in the medical literature, especially in the epidemiology side of things, is that if you were to look at an exposure to a risk factor, what is the influence of that risk factor on causing disease? You know, are some things protective or some things harmful? And so there's lots of different ways to go about this this sort of problem. And two terms we're going to use to describe these types of studies. One is going to be incidence. This is going to be basically the rate of new cases of disease as they go through a period of time. Look at some examples of how we use those. And then prevalence is basically the fraction of a group that has a disease. And so there's a few different types of studies we can do that look at incidence and prevalence of patients who have a particular risk factor and then whether or not they have the disease. The first one being a cross-sectional study. And basically this would just be you take a group of people, you take a single sample of subjects, how many people you want, and you select them without either regard to whether they had the disease in question or the risk factor, right? You're just taking a cross-section of people at a given time. And basically what you're going to do is you divide those two groups of people based on whether they've had previous exposure to the risk factor. So maybe smoking, could be asbestos exposure, could be lots of different types of risk factors. And then basically based on their exposure, as you put them into two different groups, you're going to look at the prevalence of disease, or basically the proportion of people or fraction of people that have that disease at that time. And so then from there you can start to do some statistical tests to determine whether or not that risk factor really had an effect on the number of people that had the disease. That's one way to do it. Basically a cross-sectional study. Again, you're just looking at a single slice of time. You can also look at prospective studies, where essentially what you would do is you, instead of just taking a group of people without regard to exposure or disease, here you're going to get two groups of people, two groups of subjects, and you're going to basically divide them kind of at time zero. One group is going to have exposure to whatever your risk factor is, and the other group is going to be the non-exposed, right? They're going to be kind of your control group. And so basically you would observe them over time to determine which of those people, based on their risk factors, develop the disease in question. So for instance, you would have, say, for instance, I selected a random group of people, went out to the millennia, and I recruited people for a study, and I said, okay, smokers go into one group and non-smokers go into another group. And then I were to observe them over the next 5 years to see who developed lung cancer, right? The number of people developing lung cancer as time went forward would be considered our incidence rates, right? Because those are new cases of disease going forward. So that's a prospective study. Again, you start at time zero and you kind of go forward in time. So then also another type of study you may see is an experimental study, where basically we'll have a single sample of subjects, and they were kind of selected randomly and then divided into two groups. And so this is going to be more of kind of what you might think of like drug trials and things like that, where basically each group either gets a different treatment, or you may have one group getting a treatment and then the other getting no treatment, right? So you have a controlled trial where you have that control group, and basically you would look at the outcomes or the incidence of disease or certain outcomes as time moves forward. So again, you can kind of think of prospective and experimental studies kind of being lumped together as looking, starting at time zero and then kind of moving forward to see what kind of outcomes you discover based on either risk factors or based on what type of treatment you give them. Another type of study you've probably heard of is a case control study, and this is where we get two groups of subjects that are selected, and basically we divide them up based on if they have the disease or not. So if we were going kind of with the smoking and the lung cancer example, we would take patients with lung cancer and patients without lung cancer, and so those with the disease are considered our cases, and we would match them typically with people who do not have the disease, right? So those are our controls. And so what we do at that point is we look backwards in time. So this is a retrospective study where we go backwards and see what type of risk factors were associated with developing that disease, right? So we're kind of comparing people without the disease versus those that do have the disease and saying, well, how did the risk factors differ? Was the number of people smoking, did that have a big influence on who ultimately developed the disease or not? And so that's another way to do that. And again, the benefit here being retrospective, you can look backwards in time instead of having to, say, do a study for 5 years. You can do this just in one sitting, essentially. So let's look at an example of an experimental study. Here's a clinical trial where this is back in 1993, and what people were doing was looking at the effectiveness of zidovudine, which gets abbreviated as AZT. It's an antiviral medication used to treat HIV. And they wanted to see whether treating asymptomatic people that were infected with HIV and with a normal CD4 count, if this had any kind of influence on outcomes. At that time, we knew that AZT was effective for patients with AIDS and asymptomatic patients with HIV with a low CD4 count. Because remember, AIDS usually is a secondary effect of having HIV. It's usually when you have some sort of AIDS-defining illness, like an opportunistic infection or something like that. So we knew AZT worked for patients with more progressive HIV/AIDS. We know patients with low CD4 count who are asymptomatic also tended to benefit from having AZT. And so what we did, or what they did at the time, was they had HIV-infected adults. They were assigned to either receive AZT or placebo, and then they were followed for 3 years to observe disease progression. In this case, what they were looking for were either symptoms of disease or a drop in their CD4 count. Okay, and so the question was, does treatment with AZT reduce the progression of the disease? Okay, and so this was considered to be a randomized, double-blind, prospective study, right? So there's a couple of things we can break down from that. So again, nowadays you may be thinking, well, that didn't sound very ethical to have someone with HIV to not receive medication. But think back, this was going on greater than 20 years ago. We didn't really know at the time if AZT was really going to be effective for these individuals. So this is at a time where we didn't know that treating patients who are asymptomatic with a high CD4 count was actually beneficial. Nowadays we do know that it is, but we'll kind of look at that as we go forward. Anywho, and so you can also gather from this is a prospective study because they're starting at basically time point 0, having patients into these two groups, and then kind of moving forward in time to see if they determined or developed any of these outcomes. This was randomized. Are considered randomized because patients were randomly assigned to either receive AZT or placebo, right? You're going to find that by doing this randomization, you try to eliminate some of the bias that can be entered in. That way, you can be assured that people in both groups are going to be randomly assigned there, so that way you can kind of eliminate sicker patients being in one group versus another, or try to eliminate some of those kind of biases there. Again, this is considered a double-blind trial because the patients were not aware if they were receiving AZT or placebo, and also the investigators, when they were evaluating patients, did not know either. Because again, if you knew that someone was receiving placebo, you may be more likely to see, hey, are they developing symptoms, or you may be more likely to make certain observations, versus if you had no idea if the patient was receiving drug or not. So what they basically found was, and they took a look at all the outcomes, and again, outcomes being disease progression, which is either symptoms of HIV/AIDS, or if they had a drop in the CD4 count. And so they looked at the treatment with AZT or placebo, and they were looking here at whether the disease progressed, or they had no progression in these cases, right? So again, you have your totals column. And so here, one of the things we could do is we could look at a chi-square table. We could look to see, these are our observed frequencies. We could also figure out what the expected frequencies would be and come up with a p-value to determine whether or not we think that by chance alone we would see a discrepancy here this large or larger. So looking at this, they found that disease progressed in 16% of the patients who receive AZT, so roughly 76 out of that total of 475. And then for the treatment group, they saw that the 95% confidence interval, so if you were to say apply this information back to the entire population of patients with HIV who were asymptomatic, who had high CD4 counts, it would range anywhere between 13 to 20%. Okay, versus the disease progressed in 28% of patients who ended up receiving placebo. In this case, 129 out of 461. So the groups are pretty evenly matched, 475 versus 461. And so they saw here it was 28% if they received no drug. And here the confidence interval ended up ranging from 24 to 32%. So again, if you were to apply this back to the whole population of HIV patients who are asymptomatic with high CD4 counts, you would expect with 95% certainty that anywhere between 24 to 32% of them would have disease progression, as defined by the researchers. So one of the things we can do is we can start to look at the attributable risk, right? So what is the risk of having disease progression in this case? And so we see that disease progressed in 28% of placebo-treated patients and only 16% of AZT-treated patients. So basically what you can do is just subtract these out, and you can see that basically there is a attributable risk or an absolute risk reduction. I'm sure some people have heard of that term before, of 12%, right? So if I receive AZT, versus not receiving AZT, I would have a 12% reduction in risk of having disease progression. Okay. Now, one of the other things you can do here is actually get a 95% confidence interval for this number as well. And so basically we see that that could range anywhere between 6.7% up to 17.3%. So the risk reduction could be as small as a 6.7% reduction, or it could be as high as a 17.3% reduction. And here the p-value they determined was less than 0.001. Okay. And so we know that would be significant because essentially here, if we were to say our null hypothesis would be that there's no difference between treatment groups, you would expect to see an absolute risk reduction of 0%, if there's no difference. And so because this confidence interval does not cross 0, we can say that this would definitely be significant without even looking at the p-value. Okay, so basically going off of these assertions, we can see that if we assume that subjects represent the larger population, which again the people running the study have hopefully done a good random sampling of the population, we can see that asymptomatic CD4 stable HIV infected persons would be 95% confident that AZT treatment would reduce the progression of disease anywhere between 6.7 to 17.3% versus receiving nothing by itself. So again, that would be the range of risk reductions they can have based on receiving AZT versus nothing. So the question is, another thing when they're trying to determine how good is an intervention going to be, you come up with what we call the number needed to treat, or essentially how many people would I need to treat with zidovudine or AZT in order to actually make a difference. Okay, so we get this term number needed to treat here. And so what this essentially is the reciprocal of the absolute risk reduction, or in this case, reciprocal of 0.12 or 12%. And here what we find is 8.3. What that means is that for every 8 patients who receive treatment, you would expect to have disease progression be prevented in 1 patient. And so once you have a number needed to treat, you can start to compare different types of treatments to determine well, which one has a larger or smaller number needed to treat. And essentially, you would prefer to have a lower number needed to treat, right? You want to, ideally you'd have a number to treat of 1, where every patient I were to treat, they would have prevention of disease progression, right? Larger numbers tend to mean you need to treat more people before you'd actually see 1 patient benefit from that. And we can see that based on the confidence intervals, the number needed to treat could range anywhere between 5.7 to 14.9%. Okay, so that would mean that if I was to treat these patients with AZT, I would expect either 1 out of 6. Basically every 6 patients I were to treat, I'd prevent 1 from progressing, up to every 15 patients I were treating prevent progression in 1 of them. So again, we generally prefer lower numbers needed to treat in order to make sure that we get more kind of bang for our buck when we're treating all these different patients. Another thing we can look at is what we call the relative risk. And so instead of just doing a simple subtraction of one risk from another, we can actually look at the proportions. So here we're going to see the ratio between 2 proportions. And again, we're going to look at progression in the treatment group versus progression in the placebo group. We can divide these out to see the risk, which was 16% in the treatment group versus 28% in the placebo group, or basically 16 divided by 28, it's going to equal 0.57. Basically what that means is that subjects treated with AZT were 57% as likely as placebo to have the disease progression, right? So it's almost cut in half was their risk of disease progression based on this risk ratio. Okay, a relative risk between 0 and 1 means that the risk is going to be decreasing with treatment. So it basically means that with a 95% confidence interval, they can see that the relative risk was anywhere between 0.44 to 0.74. So this means basically that my patients who received treatment were anywhere between 44% as likely as placebo to have disease progression, all the way up to 74% as likely. Okay, so still a benefit, right? And the other thing here is when you're doing ratios between one number to another, now your point for significance turns into 1. So before, when we were looking at absolute risk reduction, we saw that the confidence interval, when it did not include 0, that means that we were able to find a statistically significant difference, right? Our p-value is less than 0.05. And here, because we're doing a proportion, again, if there's no difference between treatment versus placebo, what we would see here is we'd see 28% over 28%, right? There'd be no difference between the getting drug versus not. And so our relative risk would be 1. Right? So again, when I have a confidence interval that spans between 0.44 to 0.74, because it does not cross 1, that means I would also have a statistically significant difference here. Okay, so those are going to be important factors to remember, whether or not you're looking at an absolute difference between two proportions or you're looking at an absolute ratio between those two. So again, calculating our p-values here, basically all of our p-values are starting off with that null hypothesis that in this case the AZT does not alter the probability of disease progression. And so basically we're answering the kind of question that if the null hypothesis were true, what is the chance that just random sampling of subjects would result in the incidence rates as different or more so than what was observed, you know? Because again, if you did another random sampling of HIV patients and you were to, you know, say not give them treatment, you probably wouldn't come up with 20% again. You probably come up with something, you know, either a little bit higher, a little bit lower. And so basically we're asking that if the null hypothesis is true and that treatment doesn't change anything, what are the chances we're going to find a difference this big or larger? So again, the p-value depends on the sample size and how far the relative risk is from 1. And so essentially what we're seeing is that in this case we calculate it to be less than 0.0001, which means there's a very, very low likelihood that the results that we found were due to chance alone. Okay, this means the null hypothesis were true and that the treatment made no difference. There's less than a 0.01% chance just randomly picking subjects would have this large. It's not to say that it's impossible, but it's very, very unlikely due to chance alone. So in those cases, we'll be able to say that yes, AZT is very likely to prevent disease progression, and that was what we found to be certainly true. And nowadays we have even more robust treatment options for patients who are asymptomatic. And in fact, one of the things we'll learn when we get to talking about HIV and pharm is that patients, regardless of what their CD4 count is, now we treat all of them, right? Because we know that by treating early, you prevent disease progression and extend life. But moving on, now let's start to compare proportions. Let's look at some of our case control studies. So another example here would be a question, does the cholera vaccine work? So here's a study done in 2005 to try to determine this question. And so what they did was a case control study. And again, this is retrospective, meaning they start at time point, like say they started right now, started the study today, and they're looking backwards in time. And so basically they're going to be comparing whether people with the cholera were less likely to have been vaccinated than those who did not get cholera. And so we can make a table where you can see people who received the vaccine versus did not receive vaccine, and then look at the cases of cholera versus those that are controls, basically those who did not have the disease. So again, they started at time point 0. They looked at patients and divided them as to whether or not they had cholera or not, right? So they had a total of 43 people with cholera, and they had a number of controls. Typically in these kind of studies, you're going to have several controls for every single case that you have. So again, seeing a ratio here of near 4 to 1 is not unusual. So that way you're able to kind of weed out a lot of biases and whatnot. We'll talk about that more later when we get to different types of study designs, but essentially just know that you typically have more controls than you do cases when you do a case control study. But essentially, what we're going to see is when we have those patients with cholera, we're going to divide them up based on their risk factor. And so in this case, the risk factor was whether or not they received the vaccine or not. Okay. And so then we can look back at the controls. We can also divide them up whether or not they received the vaccine or not to see if there's any true differences here. So there's going to be some differences when we're looking at something like a prospective study versus one of these case control studies. And so one of the big differences here is that we're not going to be looking at relative risk because basically the information would be kind of meaningless because one, the cases and controls are not really even. We saw with that AZT trial that the comparator group, the control group versus the experimental group, they were almost similar, very, very similar in their N, right? Their sample size is very similar. Here we're not really trying to do that because essentially I mentioned that we're going to see multiple cases or multiple control numbers for every single case that we have, and so the N's are not even between there, and also we don't really have information on the entire population when we're looking at this stuff. And so based on this, and because it's not really a random assignment of these patients, we're looking to see who got cholera, who didn't, and then we're putting them into their various groups, right? And so because we were looking backwards in time as well, we can't really look at incidence, because incidence is requiring that we're looking kind of forward in time for new cases of disease. What we're instead going to be looking at is going to be looking at prevalence. So here we're looking at the prevalence of people who basically got the vaccine versus those that didn't, and how that influenced whether or not they had the disease. And so basically any kind of relative risk you were to calculate from this would really be invalid. Instead, what we're going to be looking at are going to be odds ratios. So the odds ratio is going to be the best way to summarize data from a case control study. And so one of the things to keep in mind is the difference between probability versus odds. And so essentially what we're seeing is that probability that an event is going to occur is basically the fraction of times that you would expect to see that event in many different trials. So for instance, it's going to range from anywhere between 0 to 1, because based on that percentage or that fraction you're going to get there. And so on the flip side of that, you're going to see that the odds get defined as the probability that an event will occur divided by the probability that the event will not occur. So basically, odds can be any kind of positive number, or it could be 0 if there are 0 odds that something is going to happen. But essentially, what we can see is that we can convert probability to odds basically by dividing our probability by 1 minus that probability. That sounds confusing, but essentially another good way to look at this would be horse racing. And so in this case, we can see that we have a horse that runs 100 races and basically wins 25 times. And so the probability of that horse winning a race is basically 25%, because it's 25 out of 100 total races there. And so if we wanted to convert that to odds, basically we'd say is the odds of that horse winning a race would be 25% divided by 1 minus that 25%, or basically 0.25 divided by 1 minus 0.25. And so when you divide that out, it becomes 0.33, which basically means the odds of that horse winning a race is 1 win for every 3 loses, right? Or 3 losses, I should say. So again, the odds ratio is going to be the best way to summarize data from a case control study. And so what we can look at are basically the cases of people who got cholera. We can look at the odds of them being vaccinated versus not being vaccinated. So in this case, we had a total of 43 people who in the study who had cholera. 10 of them were vaccinated versus 33 of them which were not vaccinated. Or in this case, we saw that had a odds of 0.303 of getting cholera if you were vaccinated. And so if you look at the among the controls, the odds of being vaccinated were 94 to 78, or basically 1.205. So what we can do is, because we have these two different odds, we can look at an odds ratio and determine our answer. Does the cholera vaccine prevent cholera? And so the odds ratio here is 0.303 divided by that 1.205, or basically 0.25. And so when you get the 95% confidence interval, you can see here that it ranges between 0.12 to 0.54. Again, because we are doing a proportion, we're dividing one odds versus another. Our cutoff point for significance is going to be 1 again, because if there was no difference, if the vaccine made no difference in getting cholera or not, you expect to see an odds ratio of 1. So because this 95% confidence interval does not include 1, you can see that this would be statistically significant. Okay. Basically, what this means is that we conclude that vaccinated individuals are going to be 25% as likely to get cholera as unvaccinated people. Okay, and so in this case, in certain vaccination studies, it would also make sense to kind of do the flip of this. And so basically, we can subtract the odds ratio from 1, or basically 1 minus 0.25, and we get odds ratio of 0.75, meaning that the vaccine is 75% effective in preventing cholera. So again, the question of whether or not we think this is going to be truly preventative by vaccinating people, it would appear that this would be the case, and it would be statistically significant based on the fact that this odds ratio did not include 1. So again, with the odds ratio and its confidence interval is usually going to be accompanied by a p-value. Again, the null hypothesis in this situation would be that there would be no association between getting vaccinated or people who are vaccinated and the cases of cholera or not, right? So there should be no difference between those groups. And so here we found a p-value of 0.003, which means there's only a 0.3% chance that an experiment of that size would show such a strong association between being vaccinated and not getting that disease, or being unvaccinated and getting the disease. And again, in this case, we'd end up looking at a two-tailed p-value. If you guys think back for a few lectures, again, this would allow for the possibility of either less or more disease with the vaccine. For instance, if we're using, say, like a live attenuated vaccine that had the possibility of causing disease, maybe you could see it go the other way, where people who are getting vaccinated had more incidence of the disease. This was not the case in this example, so we could probably conclude pretty safely that it would appear that getting vaccinated would reduce your odds of getting cholera. So some of the advantages of case control studies is that they can be done relatively quickly and with a small sample size, because again, we can look at people who already have our cases. We already know who's going to get the disease and look backwards in time. And so you can do that, at a very short period of time versus doing a 3, 5, 10-year study, right? Some of the challenge, though, is picking the right controls. If you pick the wrong people to compare with your cases, you can run the risk of introducing bias, and you may skew your results one way or the other. The idea is you want your controls to be very, very similar to your cases in age, gender, socioeconomic status, all sorts of other things. Because if you can control for those extraneous factors that can confuse the results or confound the results, basically that may skew your data saying, hey, this looks like there's a true effect here, or maybe there's not an effect here, right? So that's one of the things we try to control for, is to make sure our cases look just like our controls, or vice versa, our controls look just like our cases. And so how do you know when to accept the results? What you find is that the results tend to be more likely to be true when the odds ratio is large, when the results are repeated, so they can do it several times, or when the results make sense biologically. I think most people could understand, if you get a vaccine, less likely to get the disease. That kind of makes sense. Okay. Next thing up is going to be comparing two means, or looking at the unpaired t-test. So the example we're going to look at when we're comparing two means here is going to be the maximum relaxation of the bladder muscles. So hopefully everyone went to the bathroom before this. And so basically what we can see is that we can do unpaired t-tests is going to help us compare two means of two separate groups. Okay, and we're assuming that the data we're sampling from is from a Gaussian population. Again, this is an example of a parametric test, which means that we're sampling from a Gaussian or normal distributed population. And so the data we're pulling, or the information we're pulling from, is Fraser, a study done in 2006, where basically we're measuring how well the neurotransmitter norepinephrine relaxes bladder muscle. And so we can look to see it at the maximal relaxation at high doses, and they can compare it old versus young rats. And so the question is, do old versus young rats differ in the degree of relaxation that norepinephrine causes on the bladder muscle, or is the difference they observe between the rats just due to a matter of chance? So basically what they did is they compared the old rats, looking at the maximal relaxation of their bladder muscle versus the young rats. They want to see, based on the means or the averages between these two groups, is there a statistically significant difference? Here you can see it graphed out. You can see the percentage of Emax. You can see here that the young rats tend to have higher amounts of relaxation, higher percentages of Emax versus the older rats. So we want to find, is this difference here, these means, is there a statistically significant difference between the two, or is this difference just due to random chance alone? So basically what we can do is an unpaired t-test, which basically means that the two groups are completely independent of one another. We'll find some examples of what we use a paired t-test for, but basically what we found was when you run this test, you see a p-value of 0.003. Now again, the null hypothesis here would be that there's no difference between the response of these bladder muscles to norepinephrine, but we can see here that the differences we observed, that's very, very unlikely due to chance alone, 0.3%, that you would see a difference this large, right, just due to chance by itself. Now, again, are the means statistically significantly different? Yes, they are, because again, the p-value is less than 0.05, so a good deal bit below that. And then, another question, is it a one or two tail p-value? Notice here it's a two tail, meaning that you could have seen the old rats have a larger degree of relaxation than the young rats. Because we weren't sure which direction the results were going to go in, that's why we want to use a two-tailed test to make sure that we are likely to basically, if we specified beforehand, we said, hey, we think the young rats are going to have a higher amount of bladder relaxation, we could have done a one-tailed t-test, but in this case, we're going to stick with two-tailed. That way, because we can just say, hey, we don't know which direction it's going to go. So again, looking at the data and how it can be graphed a few different ways, you can see here these horizontal lines are the means of the two groups. So again, you can see this difference between one another. So we saw this on a previous slide, but if you were to subtract mean B from mean A, you would see this difference here is 23.55. And that kind of makes sense based on what we're seeing here with the means. Again, notice how we're not doing a ratio of the two means to one another, we're doing the difference between them. So that means when you're looking at this value here, the mean of 23.55 with a confidence interval, because we're doing simple subtraction of one mean versus the other, the level of significance is going to be 0, which means that if our confidence interval were to extend past 0 and include 0, that means that we would not be able to conclude that there's a statistically significant difference between the two averages. Basically means we wouldn't be able to reject the null hypothesis, and we would say, hey, it does not appear to be any difference here, that it could not be explained by chance alone. But because the confidence interval does not include 0, we can say, hey, the p-value is going to be less than 0.05. We know this is going to be statistically significantly different between these two averages. So again, interpreting the results from an unpaired t-test, if we're using the confidence interval, again, we're going to see the mean maximum response in old rats is 23.5. lower than in the young rats, and the confidence interval range between 9.3 to 37.8. The confidence interval is pretty wide, but does not include 0, so we can be sure that the mean response in old animals is going to be less than the mean response in the young ones, right? So we can say, yes, there is a statistically significant difference between these two that is not explained simply by chance alone, or a very small value. If you looked at the p-value, you would see that null hypothesis is that both sets of data are going to be randomly sampled from populations with identical means, so that being old versus young wouldn't make any difference in how much response you saw in that bladder muscle. And so of course the p-value is telling us that if the null hypothesis is true, what is the chance that a randomly observing a difference is large or larger than what we observed in this experiment? And we can see here with that two-tailed p-value that was 0.003, very unlikely just due to chance alone. So some assumptions we make with an unpaired t-test. Basically, we're going to say, hey, this is a random or representative sample. Should be from Gaussian distributed data or normally distributed data. These need to be independent observations. I mean, they can't do, like, say, a before and after of the same rat. You couldn't have related rats to one another. They need to be completely independent of one another. That's why it's an unpaired t-test. We'll look at an example of what a paired t-test is in just a second. Hopefully the data is accurate. Hopefully the values are going to be distributed in a Gaussian manner. And again, we're going to see that the two populations have the same standard deviation, even if the means are going to be distinct from one another. So again, this is not always going to be an absolute, but hopefully you're not going to see wide ranges in the standard deviation or in that variability of the data. So that's hopefully something we're going to be looking at as well when we look at the results of the literature. So looking at some of these overlapping error bars in the t-test. So again, here when you're looking at these means, you see here, again, this is very similar to data what we saw before, just a different graphical way of representing it. We can see the standard deviation, how it extends up and down. But the biggest thing to note from this, looking at the standard deviations, is that just because we see overlapping standard deviation bars here does not mean that you can conclude anything about the degree of statistical significance between the means. It just means how much variability there is in the data about that mean. So again, you can see here that the old rats had a lot more variability versus the young rats. Again, this might be something you'll see represented in graphs. Again, always make sure you double check and just make sure that these are not confidence interval bars, because if these did overlap, that would mean something different if you were looking at confidence intervals. Again, remember the standard error of the mean, it has to do with the standard deviation, but also is going to include that factor of sample size. See here, standard error of the mean is typically lower than your standard deviation because it is influenced by your sample size. Again, the standard deviation divided by the square root of n is going to be your standard error of the mean. Again, because these do not overlap, does not conclude anything about statistically significant differences. Again, you can only tell that based on the confidence intervals. On the flip side, though, that if these standard error of the means bars did cross over one another, you could probably tell there's no likely chance that the confidence intervals would not overlap. So you wouldn't be able to tell anything about the, you wouldn't be able to reject the null hypothesis and say that they're statistically significantly different. Now, one of the things we can do is actually look at the confidence interval bars and see if they overlap, and that helps to determine if there's any statistically significant difference here. Essentially, what you can see is if you're looking at two different means and you're looking at the error bars, the 95% confidence intervals, if there is no overlap here, which you can see is just barely no overlap, that would lead you to believe that the p-value is going to be less than 0.05, and you'll be able to conclude that there is a statistically significant difference here between these two. So here's a nice table that kind of gives you an overview of whether or not your error bars are overlapping and what that means. Essentially here you can find the conclusion to make if the bars overlap, and so looking at standard deviation, can't really make any conclusion by looking at this, and this is true for standard deviation. If they don't overlap, can't draw any conclusions from that, because again, this doesn't really take into account the sample size at all. And then looking at standard error of the mean, which does look at sample size, you can see that if the bars do overlap, you can be pretty well assured that the p-value is greater than 0.05, and you're not going to be able to reject the null hypothesis. If they don't overlap, you necessarily can't really take any conclusions away from that, unfortunately. 95% confidence intervals, though, if the bars do overlap, the real conclusion can be drawn there. It's not necessarily going to be greater than 0.05, but if the error bars do not overlap in the 95% confidence intervals, you're going to find the p-value is going to be less than 0.05. So that's one of the big things you're going to look at. But again, it's usually easier just to look at the confidence intervals, the actual numbers themselves, and see if they cross 1 or 0, depending on if it's a difference or a ratio. In this case, when we're comparing, doing an unpaired t-test, and we're comparing two different means, because again, it's not going to be a ratio, it's just going to be the difference between two means. Using 0 as our level of significance is the thing there. So again, if the confidence interval does not include 0, then you can conclude that yes, there's a statistically significant difference there. So if we wanted to compare two paired groups, on the other hand, and I'll show you some examples of what that means, we're going to use what we call a paired t-test. So the paired t-test, what this is going to help us to do is to compare, say, two matched or say paired groups when the outcome is going to be continuous. Again, as we're using continuous variables here. The experiments are going to be designed so that you're either looking at the same patients or say like the same experimental preparations, usually in a before or after intervention kind of scenario. So say, for instance, you're measuring patients' blood pressure before they receive treatment and say after treatment, right? Because it's the same patients, you need to take that variability into account. It would not be appropriate to use an unpaired t-test because again, unpaired t-tests assume that all the patients are not related to one another. And then it's not going to be appropriate to use non-parametric tests. And again, non-parametric tests are going to be dealing with data that is not considered to be normally distributed or a Gaussian distribution. So unpaired t-tests are going to be not really distinguishing about variability among subjects. It's assuming all the subjects are independent of one another, versus these paired t-tests can help us to distinguish that if we do see differences, is it due to differences with the patients themselves, or is it going to be due to the actual treatment that we're interested in? So again, when subjects are being matched together, so say you have like siblings, twins, something like that, or they're going to be paired, the same person, say before and after, you have to use a special pair test that will be used. So for instance, you're using a variable measure in each subject and a before-after intervention, as I mentioned, with like say hypertension treatment. If you recruit subjects as pairs, they're going to be matched for variables, meaning that for instance, you match people based on their income level, their height, their weight, their disease states, all of that stuff. Basically, you give one person an intervention, the other person not. That would also be another case for using a paired t-test. Twins or siblings would certainly be recruited. If they were recruited as pairs, should receive different treatments. That would be a good candidate for using a paired test. And then, say for instance, you're running a laboratory experiment, and that you have, say, a control and a treated preparation that are handled in parallel. Or say, for instance, using part of the body on one side gets treated with a control, and the other side is the experimental treatment. So you have some sort of like say topical treatment on your left arm versus your right arm. And then if you're looking at the same subject, having measurements performed with two different methods. So if you were to say looking at differences in blood pressure measurements, say with manual auscultation versus like an automated machine, that'd be another candidate for using a paired t-test. So a good example of this would be a study done by Charles Darwin back in 1876, who was looking at the growth of plants from seeds that were either self-fertilized or with seeds that were cross-fertilized. And so basically they were controlling and pairing seeds based on changes in soil, temperature, or sunlight. So this would be a case because we paired them, and they're getting two different treatments. We can use a paired test here. Here you can see the results when you're comparing those plants that were cross-fertilized versus self-fertilized, and you can see the differences here. Okay. So basically, this is the graphical representation of the data here. So basically, these different points are going to be the difference in height between the cross-fertilized plants minus the self-fertilized plants. And so if you were to see, say, a negative number here, that would mean that the self-fertilized plants grew larger than the cross-fertilized plants. But you saw the majority of plants ended up growing more in the cross-fertilized setting. So you can see the average here. Again, the average greater than 0, so that generally mean that on average, the cross-fertilized plants grew larger than the self-fertilized plants. And here you can see the average here, the difference in height with the standard error of the mean, kind of the upper bounds being marked there. So when they did a paired t-test, they found that the value, p-value is 0.0497. So the question is that significant? And you would say yes, it is, because the p-value is less than 0.05, just barely, but it's there. And again, because they weren't sure which plants would grow better, they had to use a two-tailed p-value there, right? So that way they could be sure that if either one ended up growing more than the other, they could kind of account for those differences and be able to show significance there. Again, lots of other information we're going to cover to some degree in some later sections, but just be aware that yes, this was significant, and the reason why we used the two-tailed value here. So interpreting these results, by looking at the confidence interval, you see that a paired t-test is going to be looking at the difference in measurements between those two matched subjects, or if we were looking at a measurement, say, before and after. So again, each of those pairs are going to be looked at individually and then kind of compared with the entire group. And so for this example, we saw that there's an average difference in the plant length between the self and the cross-fertilized plants by about 2.62 inches, or about 15% or so. Now again, because we are looking at the, subtracting one mean from another, we can look at the 95% confidence interval and see how it ranges between 0.003639 up to 5.23 inches. And because it does not include 0, we could conclude just from looking at the confidence interval that this is statistically significant. This is less than 0.05. It's just barely, because it just barely does not include 0, but it's there. And so this would conclude with 95% confidence that cross-fertilized seeds grow larger than your self-fertilized plants. Okay, notice how the confidence interval is pretty wide. So perhaps if we had done this with a larger sample size, we could have narrowed down those confidence intervals and been more sure about our conclusions. So again, our p-value is telling us that if the null hypothesis is true, there's no difference between the height of the two kinds of plants, that the differences we see is just due to chance alone. And again, the p-value is 0.0497, so just barely achieving significance, but it is significant. And again, why would you use a two-tailed test? Again, because if you weren't sure which way that was going to go, which ones are going to grow larger, you have to kind of go with the two-tailed test. Otherwise, you have to state out prior to the experiment and say which one you think is going to grow larger, and then be able to show the p-value being significant that way. So just keep those facts in mind. All right, the next thing we're going to be looking at is correlation, and of course how that relates back to causation. So next thing we're going to be looking at is correlation coefficient, or this variable r is we're going to look at. And so what we can see is that by associating two continuous variables together, we can quantify how well they correlate based on this r value. Okay, so an example of a study here was back in '93 with this fellow named Borkman. He hypothesized that the lipid composition of cell membranes on the skeletal muscle affected how sensitive the muscle was for insulin. And so basically they took 13 healthy men and they were trying to determine their insulin sensitivity. So what they did was they infused insulin at a standard rate, and they tried to quantify how much glucose they needed to maintain a constant blood glucose level. So the more sensitive the patients were to insulin, the more glucose they'd have to infuse in order to keep that same level. The more resistant they were to insulin, the less glucose they'd have to infuse. They also took a small muscle biopsy of each of the subjects and measured the fatty acid composition. And so they were focusing on these percentages, these polyunsaturated fatty acids between 20 and 22 carbon atoms. So basically the percentage of polyunsaturated fatty acids they had on that skeletal muscle between 20 and 22 carbon length, or 20 to 22 carbons long. And so what you'll find is that both variables tend to be scattered, and I'll show you the graph in a second here, but the mean insulin sensitivity index is 284, and we saw that there's a standard deviation of 114 milligrams per meter square per minute. Again, the meter square is based on the size and the height of the patient, or the weight and the height of the patient, and then we're going to see this is basically the amount of insulin that's having to be infused per minute based on their height and weight in order to maintain that standard glucose concentration. Again, they found a coefficient of variation is going to be 114 minus that, or divided by that standard deviation, and you saw it's 40.1%, which is pretty high for the most part. So you saw there's a lot of variability there in that data. And so again, authors knew the variability was going to be inevitable, and so they tried to look for some reasons for this. And again, keep in mind this is only with 13 individuals, so hopefully if we had more people, you might have been able to try to get a little bit more consistent values there. But what they saw was that fatty acid content is less variable, with a coefficient of variation of 11.6%. So much less variability here seen with that. And so in the graph, they were looking and they saw a clear relationship between the two variables. Basically, individuals who have more of the polyunsaturated fatty acids between 20 and 22 carbons long tend to have a higher insulin sensitivity. I mean, they need more glucose, meaning they're getting more of it's being shuttled into the skeletal muscle. And so we can see there's going to be some variables that vary together, or these variables do vary together. So we call this covariation or correlation. So here's just a table showing the insulin sensitivity of the different individuals, and then looking at the polyunsaturated fatty acid percentages here. Okay. So the important thing you want to look at is to look at basically these graphs, and you want to see how much these two variables vary with one another. So basically what you can do is you can put one variable on the x-axis. So here you're going to see the percentage of 20 to 22 carbon-linked fatty acids here. And then on the y-axis we're going to have insulin sensitivity. And so what you kind of notice is that it's not completely random. It looks like if you had to draw a line right through here, you could probably do that, right? If you had to draw an average line between these two. And so that's what we're looking for, this coefficient of are looking for this correlation coefficient. That's at R values, how straight of a line you can basically put through here. So again, when we're looking at the direction and magnitude of that linear correlation, it's going to be quantified by that coefficient, and the value can range anywhere between -1 to 1 depending on the slope of the line. What we'll see is that if the correlation coefficient is 0, then the two variables do not vary together at all, which basically means that it would be basically a straight line. There's no variability in one variable that you could explain by the other, essentially. If you have a positive correlation coefficient, it tends to mean that the variables tend to increase and decrease together, so they're going to be proportional to one another to some degree. Versus if it's negative, it means the two variables are going to be inversely related, meaning that as one goes up, the other tends to go down. And then if the value is between 1 or -1, the two variables tend to vary together completely, and it would graph as a straight line. So if it was, again, if the value is 1 or -1, that means you have complete correlation there, that any increase in one is going to cause an increase in the other, vice versa. And so in our example here, we saw that we're probably not going to get a completely straight line, but our R value is going to be 0.77. So just to show you a couple examples of what different R values would look like. Again, with the R value -1, you see that again these are going to be inversely related. So as one value was increasing, the other value would be decreasing. Again, it's a straight line. As you get closer and closer to 0, you're going to notice that there's going to be more and more scatter of the data to almost completely random, and you can't really figure out what kind of linear relationship there is with one another. As you start to increase that correlation coefficient, you're going to start to notice it get tighter and tighter until eventually it's going to become another straight line. So our values we saw was about 0.77, or which is pretty close to what this one looked like, and that makes sense. So again, as the percentage of polyunsaturated fatty acids went up, we saw an increase in insulin sensitivity for those patients, right? So when looking at this, we'll see that the 95% confidence interval for the correlation coefficient is going to range, in this case, between 0.38 to 0.93. Again, notice these can tend to be asymmetrical depending on how the data lines up. But because we're looking at this, it does not include 0, because again, 0 would be that there's no relationship between one variable to the other. We can say that yes, this would be statistically significant, right? So there is some degree of correlation between these two values. If you're looking at the p-value, it means it was 0.0021. And so in this case, the null hypothesis is going to be that there's no relationship between insulin sensitivity and the lipid composition of those membranes. And so in that case, we would say that the correlation coefficient is 0, right? There's no relationship between one another. So again, we're looking at a two-tailed value because we don't know if the R value is going to be positive or negative. But because we're looking at this, we can reject that null hypothesis because the chances of having correlation that good of 0.77 is very unlikely due to a chance alone. Again, 0.21% due to random chance that we would see a correlation that good. So looking at the relationship between correlation and causation, I'm sure you guys are very well aware that correlation does not imply causation. So one does not necessarily predict the other in these cases. So the question is, why do these two variables tend to correlate so well? Does the lipid content of the membranes determine insulin sensitivity? That's one possible explanation. Perhaps the insulin sensitivity of the membranes is somehow affecting the lipid content. It could be the other way around, where one is begetting the other. And then perhaps we can find that insulin sensitivity and lipid content, they're just under the control of some other factor altogether. Maybe there's some other hormones that we're not necessarily looking at. Okay. And then, looking at lipid content, insulin sensitivity, all these other factors, it's probably pretty complex network of feedback mechanisms and et cetera, genetic controls, things like that. And so, we could just be getting a look at something that's much more complicated than just, these two variables together. So again, it could be complete coincidence that these are correlating with one another. But what we've seen with that p-value is that yes, they do correlate with one another, but we can't say that there is any kind of causation between these two. Again, oftentimes it requires a lot more research before you can really answer that question. So just keep in mind that any two variables can certainly be correlated without having a direct causation. So for instance, in older studies, they used to look at the number of telephones per capita and saw that correlate with increased life expectancy. Certainly we don't believe that having more telephones should increase your life expectancy, but there's probably something else going on there, like either socioeconomic status or different things like that. So just keep in mind, with all statistical tests, some assumptions are going to exist, and this is one of the biggest ones, is that you do not want to correlate. Just because there's correlation does not mean causation is involved here. So again, with our assumptions, when we're looking at correlations, you're again going to be assuming that you're working with a random sample. And here we're also going to be working with paired samples. So it wouldn't make sense in the example before if we were using insulin sensitivities from different people than what we were looking at for the carbohydrate or the carbon chain fatty acids, right? Again, you should be sampling from one population. There should be independent observations from one another, and then any values used, none of the x values are going to be used to compute the y values, and vice versa. So again, one should not have a direct effect on the other one. There should be an independent set. And then again, the x values are not going to be experimentally controlled. So again, whatever distribution is there, like that needs to be seen, so you don't want to have the experimenters control for that sort of thing. And then we're going to see that both variables follow Gaussian distribution, right? So you can test for normalcy for both of those to determine if it seemed like it was being pulled from a normally distributed sample or population. And again, you're going to find all covariation is linear. So again, this is going to be a linear correlation. You should not be able to find any kind of curves. This is going to be more kind of more complicated statistics we may see with some of the different types of regressions and things like that we'll talk about later. And again, you do outlier tests. Again, outliers need to be kind of accounted for, but typically you're going to should have no outliers when you're applying for these correlations, because that can skew your data pretty significantly. So another value we can see is our R squared value. And so if we take the square of the correlation coefficient, this is actually becomes an easier value to interpret than just the R. Because R is always somewhere between -1 and 1, R squared is always going to be a positive number between 0 and 1. And so by looking at the R squared, it's going to be the fraction of the variance shared between the two variables. And again, correlation is going to be used here in the strict statistical meaning, but it's going to be quantifying that association between two continuous variables, whether it be interval or ratio, doesn't really matter as long as they're continuous. Again, this is oftentimes used kind of more in a general sense of the term, but when we're talking about the R squared value, that's also called the coefficient of determination. And again, that's telling us the percentage of variations explained in one variable via the other, right? So again, we would see if R squared value was, say 0.77, that means there's 77% covariation between those values. So just finishing up, looking at this, can the t-test be computed from the mean, standard deviation, and sample size of each group? Why is it called an unpaired t-test? And it doesn't matter whether two groups have different numbers of observations. So can a t-test be computed from the mean, standard deviation, sample size? Absolutely. You don't need the raw data necessarily. You just need to have an idea of what the mean is, and also some of these other factors here to figure out what your confidence intervals and et cetera are going to be. Unpaired t-tests are called that because the values in the two groups are not matched. They need to be independent of one another. If they are going to be matched, you can use a paired t-test, and that tends to be more powerful to look for any of those differences there between within the individual participants. And it doesn't matter whether the two groups have different numbers of observations. No, typically you're going to find that the t-test does not require an equal n. You're going to find that t-tests tend to be more robust to violations of that Gaussian assumption when the sample sizes are equal or at least nearly equal to one another. So it basically means you're less likely to make type 1 or type 2 errors if you have a pretty close sample size to one another, because as you get to large differences in your n, you're more likely to have issues where you're dealing with, say, non-Gaussian data. Can I decide how the subjects are matched after collecting the data? Does it matter which variable is called X and which is called Y in a correlation calculation? Can R be negative? And if you double the points but R doesn't change, what happens to the CI and the p-value? So can I decide how the subjects are matched after collecting the data? Absolutely not. This needs to be done a priori, meaning you're doing it before or while you're setting up the experimental protocol. If you're doing it afterwards, you're just kind of looking for things that look good, and that introduces too much bias and finding kind of false positives in those cases. Does it matter which variable is called X and which is called Y in correlation? No, you'll find that you can switch them interchangeably, and you're going to find that get the same results, should be symmetrical in those calculations. Can R be negative? Yes, it is negative when one variable tends to go up as the other goes down, when they're kind of inversely related or correlated to one another. You're going to find that R squared is only going to go positive because of the fact, or 0 to positive, mainly due to the fact that it's going to be squared. So any negatives will be canceled out there. And if I double the number of points but R doesn't change, what happens to the CI and p-value? You typically find that the confidence interval is going to get narrower because, again, I have more data to show this is probably closer to the actual population, and the p-value ends up getting lower. So, again, less likely that whatever I do find is going to be due to chance alone. All right, so that concludes it for this presentation. We'll go ahead and continue on in the next one next time you watch it. All right, thanks a lot. Have a good one.